Hey, remember when we did boxes on the ramps? And then we also did pulling or pushing an object at an angle. Well, today we're going to review that really quick. And so the key to these problems is having a quality picture. I threw together a little picture here before we started this thing, and hopefully this works out for you. I also copied the data table that I had on the review. So that's right here. Okay, so check that out. Okay, when you do that paper, it's going to be similar to this. Okay, so the first thing I'm going to do is draw my weight on here. I'm using green. I don't know why, I just am. So I'm going to go straight down because gravity is pulling that thing straight down to the middle of the earth. And I'm going to say to myself, that is the W side of this triangle to be. And because it's WMG, right? So 20 times 10 equals 200 newtons. All right, and if you're just joining me and you're not in my class, I only use 10 for gravity to make it easier. Now, would that be a negative 200? Since it's going down, you can say that if you want to. Okay, but let's just keep it at 200 right now to make things simple. All right, now the next thing we're going to do is we're going to draw a perpendicular line straight as you can do it, and then a parallel to the ramp line. Now that's supposed to be a right triangle right here, right? This side is my perpendicular, this side is my parallel. That's my symbols I'm using, and there's my perpendicular to draw that out because I didn't have that on my keyboard that I could find. Okay, let's zoom in on this thing. Now, if this angle right here is 30 degrees, that also means, and I'm not going to go into it on this paper, but that also means this is 30 degrees right there. And so what we have is an angle and a side for a right triangle. We can solve it, right? The opposite, hypotenuse. That sounds like sine to me. So 200 times the sine of 30 is going to be equal to my P. And because I'm on a roll, 200 times the cosine of 30 is going to equal to my perpendicular side. All right, I'm going to pause while I punch that in the calculator, and I'll have those numbers up in a second. Okay, I'm back. That was quick, huh? All right, so there's my numbers I have. I had for the parallel side was 100 newtons, and I had for the perpendicular side 173. Okay, so we have now our three sides of our triangle. Let me highlight that too so we have them all there. That's nice and pretty. All right, now the next thing we're going to do is find our normal force. The normal force is the force that's the ramp is pushing back up perpendicular, okay? And since there's only one force that we see right now that's perpendicular on this whole picture, and I don't have any other arrows drawn or mention anything else, the normal force is going to shoot straight up this way. And it's supposed to be equal in length, that one down there, that green one, and this is my normal force right here. And it is going to be equal and opposite to my perpendicular force because it's on a ramp and that box is not pushing through that ramp, right? Equal and opposite, so that's going to be 173 also. All right, I hope that makes sense. Now, on this paper, I also have friction negative 30. All right, let's do it. All right, so look at the picture here. We have, and I'm going to do this in a way so we can see it because I say it, and then if you can't see what I'm doing, it doesn't make much sense. But we have P pushing down the ramp, 100 newtons, right? So what that means is that friction, I'm going to draw it on my square here. So since there's 100 pushing that way, and this will be our friction pushing here of 30. Now, I have negative 30 on that paper, but I have an arrow pointing to the right here, and I have the P pointing to the left, so we know they're opposites and to subtract them, okay? So either way, it works out fine. Okay, now, what does that give us? Well, we know, and I didn't say this before, but I already said about the perpendicular and normal. They cancel each other out. this 200 newtons right here, the weight, that's already taken care of. That's been broken into the perpendicular and the parallel, right? So it's already taken care of. You don't use that number again. You just leave it be. It's broken apart. We're using its parts. You don't go back and use the whole if you've already used the parts. It's already used. Okay, enough said. All right, so we have 100 newtons down. So our net force then is going to be the parallel forces, because if we had a box on a ramp, it's going to slide down the ramp. So the directions of the forces are down the ramp, right? And then the friction is up the ramp, parallel to the ramp. So we have 100 minus 30 will be equal to our net force. Okay, I hope that makes sense. I don't know why I did that, but that's pretty cool. All right, so we end up with, what's that, 70 newtons. All right, so 70 newtons. All right, let me fill in my chart while we're here. So we have 200 here. Parallel was going to be 100. Perpendicular, 173. Equal and opposite of that, 173. Now you can put plus and minus here if you want. We have arrows pointing our direction, so I think that's going to be fine for us. All right. Then we have our net force, which is 70, and that 70 newtons is down the ramp. And so what is the acceleration? Well, we're going to F equals ma this thing. F equals ma, right? We're trying to find acceleration, so F divided by m equals a. All right, so the force was 70 newtons divided by a mass of 20 kilograms. All right, so 70 divided by 20, or however you want to break that down. I'm sorry, my calculator's off. Here we go. 70 divided by 20 equals 3.5, and the acceleration is 3.5 meters per second squared. And if you want to say down the ramp or parallel or whatever you want to show which way it wants to go, that's great. We have this picture drawn. I think it pretty much shows it as we go, though. Okay, there you go. That is very close to every single ramp and box problem you'll see. Maybe there'll be some other forces on there, but that's the gist of it. The key is this triangle right here. Okay. All right. Let's go and let's skip my Pinterest for right now, and we'll go up here and check what happens when we pull something on, pull a box on a surface. And again, I just copied and pasted that same thing I had before. So bear with me here. Okay, so let's see. I'm going to go with orange would be a nice contrast here. Here's my triangle, right? If we, in what we're doing, and I say this like every single day, if we have something at a weird angle, we can't add up the vectors because they're at a weird angle. We want them to be in a usable angle. This is a box being pulled parallel to the floor. So we want to have a vector that's going parallel to the floor. And then because there's also weight that's going perpendicular to the floor, we want to have other vectors like this side over here that we'll call the, what did I call it? Oh, maybe I don't have the right thing here, but we'll get it figured out here. We have this right here, this force right here. Let's call this perpendicular, I guess, and this parallel, right? So we have the parallel there and the perpendicular there, right? So we have those two forces because they're usable forces. That's the direction they're going to move. That's the way gravity's pulling, so it's going to work out for us. Okay, hopefully this has big enough numbers to work, because I didn't really work it out. I just took and made this up. Let's start with what we have. We have a mass of 20 kilograms, right? What's its weight? Well, gravity is pulling that thing straight down. This is the weight, WMG. Oh, I don't know where that came from. Turned into a circle. W equals mg, right? OMG? No, WMG. And that's going to be 20 times 10, because remember I used 10 for gravity, and so our weight is 200 newtons. I don't think you have to show that. I think you can just write it out, right? So you have that going on. Now, you're also going to have a force. I'm going to switch colors to maybe pink here. You have a force that's pushing up like this. Whoop. And this is going to be our normal force. We don't know what it is. We can't tell right at this moment, but we will be able to, and I will figure that out for you here in a second. Okay, let's figure this triangle out. Okay, so we have a 20 degrees, and so I'm just going to go 20 degrees, so we have to have 100 times the sine of 20, right? I'm using a calculator that for my iPhone, so it's a little different. And it ends up with sine was 34 newtons in the perpendicular. So that's pulling up. And the reason I know it's pulling up is because head to tail, for that to end up that way, the direction's showing up. So that's 34 newtons. Now I'm going to use 20 cosine. I should write that out, huh? So I went and I put 100 times the sine of 20. And on this side, I'm going to take 100 times the cosine of 20. All right, and that's how I'm going to solve those out. So this is going to be the second thing I just wrote down. And I ended up with 93 for this. Okay, and that's my parallel force. All right, what, you want to fill in numbers? Okay, weight, 200 newtons. Parallel force, 93 newtons. Perpendicular force, 34 newtons. Normal force. Okay, I'm glad you asked. All right, we have, highlight time, we have 200 newtons pulling down. So that means we have to have a force of 200 newtons going up. Look at our picture above. We have the normal going up. We have the perpendicular going up. Those two have to be equal and opposite. Sorry for pounding on the table. Those two forces have to be equal and opposite to the weight because of the picture, the way it's showing. The weight is down. So these two have to equal that to be equal and opposite. So if we take 200 newtons minus the perpendicular force 34, that should leave us, what is that, 66? Nope, 166, sorry about that. 166, right? If I make a math mistake and I don't catch it, just pretend it never happened. No, just correct it, and I think you'll get the gist of it, right? All right, so I got 166. So 166 was my normal force. Does that make sense? Equal and opposite to the forces down are the forces up. Okay, so I have 30 newtons of friction pulling that way again because I just put that on there. I drew it on there already. And what do we have opposite of that? We have a force of 93 newtons pulling to the right. Friction pulling to the left. Opposites, right? So they're going to subtract. All right, so finding our net force, F net. Why, what's that question? Why did I pick the flats? Because it's not shooting up in the air. You're pulling it across the table. If you ever pulled anything with a rope, you're not lifting it up into the sky, right? It's not going in the sky. It's pulling along the table or along whatever that is, the ground. So our direction, our net force is along the ground. It's parallel to the ground. That's where I'm getting that. So 93 minus 30, because they're opposites, equals 63 newtons. Our net force is 63 newtons. All right, F equals ma. Let me try that again. F equals ma, and we're trying to find a. So F divided by m equals a. And we're going to take and punch in that 63, which is our net force. Every time you have F equals ma, that is the F net. That's the net force that they're talking about. All right? F net equals ma. Okay, so 63 divided by 20. Again, that 20 is from kilograms because it's mass, not weight. I sound like I'm yelling at you. I'm not. So we take that 63 divided by 20. It's going to be around 3, right? 63 divided by 20 equals 3.15. And that's meters per second squared. All right? 3.15 meters per second squared. That's the ramps. I mean, that's the flat stuff, right? If we were pushing, and I'm saying this because the people who really need to see this video, they're picture is really of one pushing. The same thing happens if you're pushing. The difference is this force right here, and let me highlight that force, that's the important one, is going down. The weight is going down. So in this case, the normal force is going to be equal and opposite to the two downs, right? Because it's not going to go through the bottom of the floor. It's going to sit on the floor. And so in this case, what did we call that before? The perpendicular, right? So in this case, the normal is going to be equal and opposite. I made this symbol up. I don't know if anybody else, but that's my equal and opposite symbol. I don't know. I just made it up. Don't use it in public. People will make fun of you. Is going to be equal and opposite to the perpendicular plus the weight, because what's going down is equal and opposite to what's going up. That's the difference in those problems. Okay, I hope that makes sense. When you get into friction with these things, that increased normal force is going to increase your friction. That's why we need that normal force. All right, enough said with that. Good luck with those problems. That should cover any kind of problems you ever have on a ramp or flat.